Hello, hello. Today is gonna be, I think, a big one because I'm going to try my best to explain my understanding of structs. So there's probably, if we get to it, like some drawing and maybe some like exploration in code. So yeah, I mean, let's hope we get pretty far in this session. And also, yeah, I got some feedback on these videos, and I think the feedback is actually really good in that it was suggested that I start putting these videos in a playlist, something called like Learn C or Let's Learn C. Um, and it would actually help with future content if it just becomes more than just learning C. So, and I do want that. I want to like I have a lot of things that I want to show, and even like computer things, because this computer is like needs an upgrade, and I do want to like show I don't know, an upgrade or so. So stay tuned for that. Anyway, let's go. Structs, unions, and bit fields. Roll your own structures. Struct tequila. Oh, tequila. Tea leaves, milk, sugar, water, and tequila. Ooh, that sounds pretty good, actually. Most things in life are more complex than a simple number. So far, you've looked at the basic data types of the C language. But what if you want to go beyond numbers and pieces of text and model things in the real world? Structs allow you to model real-world complexities by writing your own structures. In this chapter, you'll learn how to combine the basic data types into structs and even handle life's uncertainties with unions. And and if you're after a simple yes or no, bit fields may be just what you need. So if you've actually messed around with other languages before, structs is like most similar to, I would say, like a JavaScript object, for example, or like in I guess C sharp and Java we'll call them like plain old objects. So they're just basically containers with a bunch of attributes, and then you just pass them around. So yeah, we'll see. We'll see after this. So sometimes you need to hand around a lot of data. You've seen that C can handle a lot of different types of data: small numbers and large numbers, floating point numbers, characters, and text. But quite often, when you are recording data about something in the real world, you'll find that you need to use more than one piece of data. Take a look at this example. Here, you have two functions that both need the same set of data because they are both dealing with the same real world thing. So then we have this function here called catalog that takes in one, two, three, four parameters. So four arguments going into this parameter list. And all it's doing is just printing everything that was given to it. And then yet we have another function here called label that also takes in the same arguments, one, two, three, four, and then just prints that out too. So the book is making a point here that both of these functions take the same set of parameters. So yeah, from a high level point of view, this doesn't look so bad, right? So that's not really so bad, is it? But even though you're just passing four pieces of data, the code is starting to look a little messy. So then you have to pass the same arguments, right? The same values into each of these functions when you call them. And that, I think, is like an opening for a mistake, because you could typo somewhere, or you can like one off some number. So yeah, and technically, like, there's only one fish, but you're making it look like there's two different types of fish, and they're both snappy piranhas, or they're both named Snappy, and they're both piranhas, but they're just the same one. There's just this little dude here. So how do you get around this problem? Yeah, so we want to be able to just pass. We want to have the notion of just passing one fish, right, as an argument, to both catalog and label, and they both refer to the same fish. So how do you get around this problem? What can you do to avoid passing around lots and lots of data if you're really only using it to describe a single thing? Cubicle conversation. Yeah, so these guys here, they don't see the problem. They think it's just four pieces of data. So let's look at the conversation. So Joe says, sure, it's four pieces of data now, but what if we change the system to record another piece of data for the fish? Frank says, that's only one more parameter. Jill says, yes, it's just one piece of data, but we'll have to add that to every function that needs data about a fish. Joe says, yeah, for a big system, that might be hundreds of functions, and all because we add one more piece of data. Yeah, so like think about it this way. If you have 100 functions that like kind of take in a fish that looks like this, right? And you add one more, like say int color, for example. Think about all the functions that you have in the system that also takes in like this type of fish. You're gonna have to add int color for every one of them. That's painful. That doesn't scale. You're gonna have to like spend the entire day just editing all your function declarations and definitions. So yeah. Frank Frank goes, yeah, that's a good point. But how do we get around it? Joe goes, easy. We just group the data into a single thing, something like an array. Joe goes, I'm not sure that would work. Arrays normally store a list of data of the same type. So that's a difference, right? Between a struct and an array. Like an array is a container too, but it's like a container of data in of the same type versus struct is a container of data of different types. But they're both, I believe they're going to be contiguous memory, right? So you'll find that like each I guess value in a struct is I think contiguous from each other, just like how it is with an array. So um, yeah, it's a good point. Frank goes, I see. We're recording strings and ints. Yeah, we can't put those into the same array. Joe goes, I don't think we can. Joe goes, but come on. There must be some way of doing this in C. Let's think about what we need. And Frank says, okay, we want something that lets us refer to a whole set of data of different types all at once, as if it were a single piece of data. So just think of it as like a container that you can just like, give to other functions. Um, I don't think we've seen anything like that yet, have we? So what we really need is something that will let you record several pieces of data into one large piece of data. So here it is. Here it is. Create your own structured data types with a struct. If you have a set of data that you need to bundle together into a single thing, then you can use a struct. The word struct is short for structured data type. A struct will let you take all of those different pieces of data into the code and wrap them up into one large new data type like this. So this is how you declare a struct. Let's actually create a project just to type that out so we can get used to it. C, we'll do structs test, and then we'll create a new file. We'll call this main.c. Pre-release version of C, C++ extension available. Would you like to switch to it? No! I'm tired of all these updates coming at me. I just want to stay on something stable. Alright, so we'll start with our template again. Ooh, how did that include stdio.h, int main, int argc, character argv, okay, and then, oops, okay, then we'll have return 0, okay, so let's declare something called struct fish, This is how we're gonna make our struct. We're gonna have const character, pointer to a character actually name. It looks like it's a const, meaning that we can't change it. It's like a label to say that we can't change the elements inside this contiguous block of characters. And then we'll have const character species. So yeah, just making sure everyone remembers we don't need this unless we want to make sure that the character pointer isn't, like, you can't modify it, right? Then you declare it as const. So we'll have int teeth, and then we'll have int age. And if you kind of look at it, right? If you kind of look at this kind of looks like a TypeScript type definition, right? So in TypeScript, it looks something like this, where we have like an interface, for example, and then we just declare like the attribute with the data type. I'm gonna just show you that. I'm using my Edge because I always use Edge now. Okay. No, you know what? I'm gonna use Firefox. Okay. So, okay, white screen. Sorry. Let's see. What am I searching for? Oh, yeah, TypeScript type definition. Not definition, interface definition. Example maybe. So something like this, right? This looks kind of like a struct, but in TypeScript. Right here, you see? Square config, color is a string, width is a number. Kind of looks the same. But then again, they're both C-like languages, right? So even though one is the OG, the C, this is a real C language here. So yeah, doesn't look too bad so far. So we're gonna have something that represents a fish with 4 properties, 2 strings and 2 numbers. So continue on. This will create a new custom data type that is made up of a collection of other pieces of data. In fact, it's a little bit like an array, except first, it's fixed length, and then second, the pieces of data inside the struct are given names. So we're not referencing them by indices anymore like arrays. We're referencing them by the property of the struct, right? So .name, .species, .teeth, .age, in this case instead of square brackets. Okay, so far so good. So once you've defined what your new struct looks like, how do you create pieces of data that use it? Well, it's quite similar to creating a new array. You just need to make sure the individual pieces of data are in the order that they are defined in the struct. So if we wanted to make a new fish, structure called snappy, this is the variable name and this is the type. Okay, so struct fish is the data type. Snappy is the variable name. And then these are the values to the properties you want to assign. And they have to be in the exact same order, and they have to fill up the struct. So we could declare something like this. So the type, struct fish, the name of the variable, or the name of the struct, and then we're going to assign values to it. In this case, we're going to assign the name, snappy. We're also going to assign the species, piranha. So snappy goes to name, piranha goes to species, and then teeth, we have 69 teeth. Okay, and then the age, 4 whatever. Okay, so we have now a struct of fish type called snappy, with the name being snappy, the species being piranha, the teeth being 69 teeth, and then age 4, maybe 4 years old. Okay. Oh, here we go. Hey, wait a minute. What's that const char thing again? Const char star, or pointer to a constant character, is used for strings that you don't want to change. That means it's often used to record string literals. Okay, so how does this struct store the string? In this case, it doesn't store the string. The struct here just stores a pointer to the string. Okay, this means that it's just recording an address and the string lives somewhere else in memory. But you can store the whole string in there if you want. Yes, if you define a character array in the string, like character name 20. Okay, so there's a big difference. If we had something like this, we are literally storing 20 characters inside the struct. Okay, but with this here, we are storing a pointer to a block of memory that will have whatever characters in the string. So I think we can just use Firefox for this. Sorry, I keep going back to Edge for some reason. Alright, Scaladraw.com. Will I have my stuff? No, I think it's an Edge. I'm sorry. That's what I get for using two browsers. Okay, let's do Excalidraw. Okay. Yeah. Okay. So let's imagine it this way. Getting the Bluetooth connected. Okay, great. Okay, so let's imagine this. If we have struct fish, and we had a const character star name, and I'm just skip the other one. I'm just saying int age. If we think about it in memory, really, the struct is only going to take up, if you have this is 4 bytes, and this one's 8 bytes only. Why? So this one will be age, which just has 4 as a value, and this is actually a pointer to somewhere else in memory. Okay, not part of the struct. Only this part is the struct. But everything else, for example, this name here is going to point to somewhere else random in memory. But that will allow us to store really, really large strings potentially, because we can go all the way up to where we have the null terminating character. So we only care about the pointer there. So in this case, the struct is 12 bytes instead. Now, if we had the other way around, where we had struct ish, I think we will just say, okay. We had something like character name 20, okay, and then int age. We take a look at our memory again. This will actually take up 20 bytes now because of this array, and then we'll have another 4 bytes, which is age 4 for the struct, and there's no pointers because we didn't define any pointers here, so therefore our struct is actually 24 bytes. So there's a difference, right? So in one case we have the 12 byte struct, in another case we have a 24 byte struct. And this is actually a struct that only limits us to 20 characters for a name. So that's the difference that they're talking about here. Okay. Onwards. Just give them the fish. Now, instead of having to pass around a whole collection of individual pieces of data to the functions, you can just pass your new custom piece of data. So we'll declare 2 functions here. Catalog, okay, struct fish f, okay, and then we'll fill in stuff here. And we'll have void label struct fish f, and we'll fill in stuff. So now notice something here. Notice how we're getting red squigglies. It says incomplete type struct fish is not allowed. Why is that? Well, it's because we're actually trying to reference something that hasn't been declared yet, right? Struct fish, when the compiler is scanning down the file, it has, when it gets to here, it doesn't know what struct fish is. So we had to actually define this before we use it. And this is already defined in main, but it, we can't see it because it's local to main. It's in local scope. So what we need to do is we need to move it out into global, and then we are able to actually have our functions see our declaration of struct fish. So we're going to do something here. Notice how we changed catalog and label to not take in those 4 parameters anymore. Like to have a 4-parameter list taking 4 arguments. But now we're just taking one value, one argument, in this parameter list, right? And the argument that will be potentially passed into this function call is going to be a struct of fish type. And it's going to contain all our properties here that we can access. Now, the hard part is, how do we even do that? How do we access it, right? So there's more code to write here. So let's write the functions, the function calls. So we'll have catalog, and we'll pass in snappy. Okay? Then we'll have label, and we'll pass in snappy too. Okay? So we're going to take, so I'm going to say this again kind of carefully as to not mislead. We're going to take this entire struct, and we're going to copy it to those functions, right? The function calls. So we're going to take all this and pass it into these 2 functions, and then we're going to do stuff with it. So, yeah. So that's how you define your own custom data type, but how do you use it? How will our functions be able to read the individual pieces of data stored inside a struct? And the tip here is wrapping parameters in a struct makes your code more stable. Because if you add something, for example, right here, int favorite music here, it doesn't change the parameter list of your functions, right? You still pass in with one single argument, which is a struct, like a fish, a struct that is a fish type, right? So, yeah, essentially that's it. So now, yeah, so we read a structs fields with the dot operator. Because a structs a little, how about I read it like this? Because a struct is a little like an array, you might think you can read its fields like an array, like this. So, what we want is we wanted to print out the name of our fish struct. You would figure that since it's the 0th index, right, like the snappy is at the first place, you'd access it at index 0. But it doesn't work that way. So we'll get an error because this is actually telling us an offset to an address. But this struct here is not exactly a pointer. Okay? So, yeah. But you can't. Even though a struct stores fields like an array, the only way to access them is by name, which is very convenient. It's easier than subscripting them with indices because it's hard to tell what you're referring to when you start using the structs. So I think it's a good thing that we refer to them by name. So you can do this using the dot operator. If you use another language like JavaScript or Ruby, it will look familiar. So just do snappy.name. Yeah. Why don't we do that? Let's do it. Let's just add a little printf here. String new line, snappy.name. And let's see what happens. First compile of the day. Oh, by the way, I restarted my computer for updates, so yeah. If it looks super clean, that's the reason why. Structs test. Okay. GCC main.c a.out. So here we have snappy. That's pretty cool. So that's how we actually refer to some property, right, inside a struct. So yeah, so okay, now you know a few things about using structs. Let's see if you can go back and update that code. Okay, so let's update it. Let's just write our code right here. I think it's easy. So we'll just want to print something. So print a string is and another string with, I guess, integer I, t. He is I. Still, what's the unit? Is it years old? Anyway, we'll have fish, f dot name, okay? F dot species. We'll have f dot teeth, and then f dot age. And let me clean this up to make it uh, readable. So we'll have this, then we'll keep it like this. Okay, so printf the string, and then everything that corresponds to each format token placeholder. Yeah. So same thing with label. Printf. What was it again? The original one. Right here. Name, species, I years old, IT. Oh, I think it's just like each new line kind of thing. Okay. So name %s, new line, species %s, new line, I years old, and %I teeth in a new line. Then same thing, right? Let's see, same thing here. Huh? Okay. So then we're going to be ending up maybe here. Okay. Then we're going to say f dot name. Did I say specifies? Alright, species. Okay. Um, let's see. What did I say? F dot species. Let's see what else. F dot teeth. And then F dot age. Okay. So that's. Oh, I flipped it. Teeth. And then age. Okay. So we have our two functions, and we've already filled this up. So let's see. Oh, we're skipping calling label for now. Okay, sure. Yeah, the solution. Name, species, teeth, age. Easy enough, and then you call catalog snapping. Let me just delete this. Okay. All right. So let's do a test drive. Let's compile our code. Do a.out, and I think we got the same result. Cool. Okay, so you've rewritten the catalog function. It's pretty easy to rewrite the label function as well. Once you've done that, you can compile the program and check that it still works. Yeah, that's great. The code works the same as it did before, but now you have really simple lines of code that call the two functions. Catalog snappy, label snappy. Same thing, we did that. Now, not only is the code more readable, but if you ever decide to record some extra data in the struct, you won't have to change anything in the functions that use it. Yeah. So we can add more properties, but our functions won't break at all. They'll only need updating if we need to use a new property. So for example, again, we had something like int fins, number of fins. We don't have to update anything in our code when it comes to functions unless we want to somehow print it out by doing f.fins. Okay, that's cool. So there are no dumb questions. So is a struct just an array? No, but like an array, it groups a number of pieces of data together. An array variable is just a pointer to the array. Is a struct variable a pointer to a struct? An array variable is a pointer to an array. So an array variable, the variable itself, right? The variable of an array, so let's just do this one again. An array of 20 characters, right? This here, when we reference by name, that is a pointer, right? A pointer to what? To a character. Character, right? But when we have a struct, say fish, right? The fish is not a pointer. So not a pointer. Okay? It's just a struct. It's a container of a bunch of properties. So that's the way to think about it for now. The way it's written. Okay? Because think of it as like any other data type. In this case, an int or a double or a long or a float. Basically, you create your own type of data with structs. Doesn't mean that you can't make it a pointer. You can, but that's like same thing with int star or long star. It's gonna be your struct star, right? So it's not like an array where this becomes implicitly a pointer. So at least the good news is that this is the only this array type of decoration is the only special case where the decoration doesn't really match intuitively how you use it as a pointer. So anyway, I know I don't have to, but could I use 01 ... to access the fields of the struct? No. Again, you can only access a struct's fields by name. Are structs like classes in other languages? They are similar, but it's not so easy to add methods to structs. Okay? Structs in memory up close. So this is an important one. Maybe we'll do another example here. So I'm going to try and read this one carefully. Structs in memory up close. When you define a struct, you're not telling the computer to create anything in memory. You're just giving it a template for how you want a new type of data to look. So again, this is just a template. Okay? But when you define a new variable, the computer will need to create some space in memory for an instance of that struct. That space in memory will need to be big enough to contain all the fields in the struct. So it's not only until you create like an object, right? And the real struct container, the object, is when you start to use memory. But when you declare one, like this template here, you don't use memory. Okay? So the assignment copies the pointers to strings, not the strings themselves. So when you assign one struct to another, the contents of the struct will be copied. But if, as here, that includes pointers, the assignment will just copy the pointer values. That means name and species field of Nasher and Snappy will both point to the same things. Oh, okay, we'll look at here later. But let's just focus on this struct. So what do you think happens when you assign a struct to another variable? So let's say we have this struct here, okay, this container, okay, and then we wanna assign this struct to another one, okay. Well, the computer we'll create a brand new copy of the struct. It's going to be a brand new copy. Why? Because structs are not pointers. They are literally like data. It's data. Okay, so that means it will allocate another piece of memory of the same size and then copy over the fields. So again, if you think about it, the struct itself will be recreated, like a new struct will be copied over, and each field will be copied over, right? From one struct to another struct. But if one of the fields is a pointer, then really technically, what does that pointer point to? A memory address. If that pointer points to a memory address, then that memory address is just going to be copied over, not the value. Because that value is elsewhere in memory, right? That's the whole point of that pointer, is to point to another place in memory. So you're just copying pointers over, not really the entire value itself. Okay? So yeah, so then if we did struct fish snappy right here, and then we made another struct called Nasher and assigned snappy to it, what's going to happen is that we're going to create two structs. Okay. However, since we have two pointers, two characters, we're just going to copy the pointer values, right? To put the pointer, the locations in memory to Nasher. In this case, both will point to the same string in memory, both snappy and Nasher. So remember, oh, and also like the ints here, since they're not pointers, they'll just be copied over, brand new copy. But technically, these are brand new copies of pointers too. It's just pointing to the same data in memory. So I really want to stress that, like, copying pointers is not copying data in memory. When you copy pointers, you're copying the address, right? The address of where they're pointing to one another. You're not necessarily copying the data. The data still stays in the same place in memory. They're going to point to the same place. Okay? So, just like here, I'll show. Okay. So, all right. Let's do an exercise. Let's do some experimentation. So let's actually start to see how a struct is in memory, how it's represented, and let's do that through code, right? So again, here's our memory. Okay. Oh, well, it looks like we'll have an extra cell. Here's our memory. So we'll just like split it up to whatever we need, and we'll just have stuff here. Okay. So when I create a struct, let's just say snappy here, and I'll just comment out catalog and label because I don't want to be confused. I want to find out exactly where the starting address of snappy is in memory. Now, I'm not an expert at this, but I do know the way to get something like an address, right? A pointer to some data is through the ampersand, right? The ampersand in front of your variable returns back a pointer to whatever. So if I wanted to create a pointer to a struct, I think all I need to do is something like this. Right? So I'm creating a pointer to a fish struct called snappy, ADDR, or let me just be more explicit, snappy pointer, right? And this gets the address of where the snappy object starts. I wonder what happens if I print F. And let's print maybe the pointer form and then the long form, the long integer form. And I'm just going to ignore the warnings here because I want to do some math. So I'm going to print out snappy pointer and then again snappy pointer. Maybe I just cast this to long. Is that valid? Yeah, the long ends. Okay. So again, the one way to get an address is through ampersand. And if we're saying that a struct is just data, just like ints, just like doubles, just like floats, right? We can put an ampersand in front of it to get the address of where this entire piece of data lives in memory, technically. And what ends up happening is that technically, this just becomes the data type star. So the pointer to a fish struct. A pointer to a fish struct. Snappy underscore PTR is a pointer to a fish struct. What does that pointer contain? Well, it contains the address of where this real snappy structure lives in memory. What address is that? Let's find out. I hope this works. Okay, so we have representation of the starting address for Snappy. This is where actually Snappy starts in memory. Cool. This doesn't tell me anything, but it tells me there's a starting address here. Right. Now, I wonder, knowing that, can I get the address of the name and the species? Well, they're already pointers, right, in this case. If I said pointer to a character, okay, and I said something like snappy name pointer, and I said something like snappy dot name, okay, that's actually valid. Because, why? Snappy name is a pointer inside the snappy structure. I want to see where that is in memory. I basically assign it like this. A pointer to a character called snappy name pointer. Now, I don't do it like this. Oops. I'm not going to do it this way. Why? Because this is already a pointer. This gets us a pointer from some value. It doesn't make sense to assign to that. Because this is already a pointer. Okay? So, doing the same exercise, let's print out what that is in memory in two forms. The pointer form, hexadecimal form, and then the long integer form, the base 10 form, essentially. Again, we're just printing out the pointer values. So, long int. And let's see what we get. Okay, that's fine. That's just a warning. It says we discard the const qualifier, but whatever. Okay. So, the pointer here is at this address. Okay? Still doesn't make sense to me. We should probably fix this too. See if we can get rid of the warning. Okay. Is this the same one? No, it's a different one. Then I did this again. Okay, cool. So that compiles. Alrighty. What happens if we do that for what is it? Snappy species. Okay. Snappy species pointer is snappy dot species. Then we can just copy this over and then change, I guess, this here to be species. Oops, specifies again. Species. And then this one here is species. Okay. That's interesting. We're onto something here. Okay. Notice something. 63 to 70. Hmm, that's about 8 bytes. Okay, so that tells us that there's an 8-byte gap. Name starts at, let's just say 763. And then species, so everything's the same, and 770. What the heck? But Snappy is like, what happens if I did this? Snappy, snappy, snappy. More than 8 characters. That's an 8-character difference, right? 811 to 836. Hmm, interesting. So what happens if I extend... Oh, it's hard to do it. How about if I do this? Do I make it longer? Huh. So it's storing stuff, right? This is where the string starts. And this is where around ends. Oh, I guess I said 8 before, but S-N-A-P-P-Y, that's actually 6. And then 7. Okay, so, okay. But notice how this is elsewhere in memory, right? It's not within this range at all. Okay? So I'm gonna actually let me keep it this way. This is actually the first time I'm doing this, so I'm just pretending I know what I'm doing, but I'm not. I'm just trying to understand the behavior. So now, what happens if I did int star snappy age pointer? I do snappy address of snappy dots age, and I think I'm supposed to do something like this, maybe. Okay, and I bet printf p ld snappy age pointer long int snappy age pointer. What am I gonna get? Oh, that's interesting. I'm back in this 140. Huh. Okay. What does that mean? Let's see. Let's do let's do snappy teeth pointer and get the address of that. Okay. Oops. Okay, so we're just doing some discovery work here. Huh. Okay. All right, so we have Snappy starting at this address 58944, and then we all of a sudden have teeth at 960. Then we have age at 964. Hmm. Well, to be fair, teeth comes before age, and so it means that 960's teeth is its memory address is coming before age, but they're 4-byte difference. And actually, I'm starting to see this, right? Like 960, 964, 4-byte difference, and they're in that same order here. Now, what do we do with this 944 thing? Well, we know that the characters, the strings, are at completely different places, right? At least the uh, the data itself. So there's a gap, right? There's a gap between 944 to 960. And let me put this in the right order. This is really hard to read. Let's see. Okay. Oops. Okay. So now it's changed again. We go to 152 to 168 to 172. So what happens in between? Since we know that these two are different data. So how do we access the base address of this then? This snappy name. Hmm. How do we do that? So because I do know that now the gap between this one here and this one here has to be both the name and the species, right? So let's do some math. 168 minus 152. Calculator. Okay, 168, oops, minus 152. 16 bytes difference. And we know pointers are 8 bytes. So we have 2 pointers in between before we hit teeth here. And we just do this. Snappy start. Snappy.teeth start. Snappy.age start. Okay. Okay, so let's try to print out exactly the address of these guys. How do we do that? Do we just do ampersand snappy whatever? Let's do it. What is this giving us back? Actually, let's take a look at this. What does this give us back? Actually, let's make an error. What exactly does this give us back? Apparently, it gives us back a name pointer. Okay. Now, let's print it out. Or a pointer to a character. How is it different? I don't get it. How is it different? Oh, what did I do? Okay. So, all of a sudden, when I print out this pointer to snappy.name, I'm just getting the address of this snappy.name as a whole. I'm right here. But that's the same thing as a struct. Okay? What happens if I do it for the species too? Oh, that's not right. Four three two 440, and I bet this is 448. Wow. Interesting. Okay, you know what? Let's focus on let's just focus on these pointers. Snappy name start. Sorry, this is so long-winded. I just think that this is like a good discovery, you know. Let me answer text. Okay, so we clean this up to kind of have a better view. Okay, so snappy start is at 304. Snappy name start is at 304. So notice how these are all the same. Okay, and then 8 bytes more, we have snappy species. 8 bytes more, we have snappy t, and then 4 bytes more, okay, we have snappy age. And that gap, 324 minus 304, is 20 bytes. So we do the math here. Is it 20 bytes? 2, 4. Oh, yeah. And then we have 4 more where it ends is going to be 328. So 328 minus 304, which is the start, right? Because this is 324 is where it starts, but then age will end at 328. So 328, where the struct ends, most likely, is minus 304 is 24. So if I do 8 plus 8 plus 4 plus 4, so 8 plus 8 plus 8 here is going to be 24. So notice how I think I'm starting to see this, right? This struct, when we create a struct, we're creating exactly what the book said, contiguous memory allocation. So this is actually 28 bytes assigned to Snappy. Okay, so here is where it starts. Right here is where our data starts, and name is actually going to point to somewhere else in memory, like we saw before, and species is going to point to somewhere else in memory, like before. But then we also have, and this is 8 bytes, right? Because pointers in a 64-bit system, the address takes up 8 bytes. It's a 64-bit number, therefore 8 bytes are necessary. And then we have 4 bytes here that stores the teeth. Then we have 4 more bytes here that stores the age. So we have address 304 here, and then we have address 312 here, then we have address 320 here, 324 here, and then finally 328 down here. Right there is 328 where it starts. So we know that when we create a struct object, we need contiguous memory to create it. Okay? But any pointer, like we saw before, which I had an accident. I didn't mean to show that so early. Um, um, they point to elsewhere in memory. And if we actually uncomment it again, okay, uncomment these 2 lines where we actually see the real data, okay, Control V, Shift I, okay, we actually see this data. Why am I getting? What's going on? Oh, yeah, where I actually see the data, it's going to be elsewhere in memory, random places, way further than the 140 whatever, right? I think it's actually less, so meaning that it is somewhere in maybe elsewhere, not in the stack. Okay, I don't know. Regardless, elsewhere in memory. So again, like the most important thing to know is that a struct is just that container of data, and memory needs to be allocated for it. Contiguous, just like an array. It's contiguous, just like an array. It's just that now we have to know the specific sizes of each field, and we know the sizes by their data types in this case. All right. Sorry for that long example. I actually didn't know what would come out of it too, but I'm glad I did it because I think we figured out that structs really are contiguous, just like arrays, but instead of referencing structs like arrays with indexes, you reference them by their field names. So, yeah. Okay, so Let's see. Do we have time? Yeah, let's do it. Okay. Can you put one struct inside another? Remember that when you define a struct, you're actually creating a new data type. C gives us a lot of built-in data types like ints and shorts. But a struct lets us combine existing types together so that you can describe more complex objects to the computer. But if a struct creates a data type from existing data types, that means you can also create structs from other structs. To see how this works, let's look at this example. So we'll have a struct here called preferences that that consists of a food character pointer and then one single field that's a float type called exercise hours. So we can actually write that here. Struct references. So we declare a new template to create a struct. Const character food floats exercise hours. I'm guessing the amount of hours this fish exercises. And then we can add a new one here, a new field into our fish that is actually a struct called care. So basically the care plan for the fish. What food the fish eats and how many hours of exercise. So you can embed, so this will point to a completely different struct, right? Like, not point. This will contain. And let's do that exercise again. Let's print out the memory so that we can see how that looks like. So we'll do that after this. So it's going to be a chunk of memory. So it's like this chunk that we allocated plus the next chunk, right? Consecutively. Maybe. That's what I think. So, yeah. So our new field is called care, but it will contain fields defined by the preferences struct. This code tells the computer one struct will contain another struct. You can then create variables using the same array-like code as before. But now you can include the data for one struct inside another. So like this. That's how you do it. You create another struct. So I'm going to fix this. So we're going to have the name, the species, the teeth, the age, and then finally inside we're going to have the care, which is another struct where the food is meat and the hours of exercise is 7.5 hours. Okay? So struct inside, and it's just, again, we access it like any other field. So once you've combined structs together, you can access the fields using the chaining of the dot operator. So take the snappy struct, go to the care property, and inside the care property, right here, go to the care property. Inside, we know that it's a preferences struct. Well, what's the template for that? A preferences struct has either food or hours. So we can print out the food as a string here. Access string. Same thing, snappy care, and then exercise hours, which is a float. So let's see how that works. So we printf snappy likes to eat string snappy.care.food and then printf snappy likes to exercise for %f hours snappy.care.exercise hours and then we can print it. Let's see. Cool. So Snappy likes to eat meat. Snappy likes to exercise for 7.5 hours. And then we forgot to make new lines, but Snappy start is here. And yeah. Cool. Okay, well, I actually want to do the same exercise with this memory address thing just to kind of see what's going on. So let's do that. First, I want to comment this out because that's just going to confuse us a little bit. Okay, so now we included an additional property called care. So we can say a pointer to a struct called preferences pointer with preferences. A pointer to a preferences struct called snappy care pointer, and it's gonna be snappy.care. And I'm guessing there's a precedence problem here, which is why I made the mistake earlier here, right? So we want to get the address of where snappy.care is at, and then snappy.care start is going to be, again, same type of format that we have. Okay, let's print it. Okay, so notice how we said age is so 8292, right? Age is int, so it's 4 bytes. So 4 bytes over 296 is where snappy care starts. And if we were to, let's say, apply the same pattern, you have snappy start here, which was 272, and the snappy name start is 272, meaning the beginning of that first property. Then we're going to say that the food in care is going to be the same address as the starting address for this snappy.care struct. So let's try that. It should be the same if because that starting point for care is actually it's also the same thing as the address the address of where the pointer of food is. So if we said something like character food pointer, and it's gonna be kind of tricky. It's gonna be snappy.care dot food. And so we print that out. Snappy.care.food start. Food pointer. Okay. And if we compile it again, warnings. Okay. So we do have the same address. Like care start is 7256. Care food start 7256. Okay, and we know there's a pointer, so it's only 8 bytes, right? It's only 8 bytes, so we should expect 264. Is it 264? 265? I don't know. To have that float, which is only 4 bytes, right? So consecutively. So we go from what is it? 232. Right, plus 8 or 232 plus 8 is 240 plus 8 more because of the pointer size, 248 plus 4 more because integer, 252 plus 4 more integer, right? It's 256, and that's the same thing as food. Now plus 8 more is like 264, something like that. So let's do it. Float pointer is exercise hours pointer. And again, we want to access the pointer. Snappy.care with the food exercise hours. Take the pointer get the address of where that exists. Okay. Snappy.care.exercise hours start. Okay, and then let's just see what happens. Warnings. Okay, was it 2-5? Was my math? Oh yeah, of course. Address changes every time. Okay. All right, so 2952, 2960. That's about right. So we know that if we were to look at all these addresses, again, they're consecutive. So when you add a struct inside a struct, all it's doing is just allocating more memory for that struct one-dimensionally. So going back here, and I wish I didn't vandalize my drawing so much. All it is that by embedding the preferences struct, you're just continuing on with this struct. So this struct became bigger. So this struct is now 8 plus 4, 12 bytes plus 24. So now it's 36 bytes. So we know that this is 4. So 2964 is when it ends, even though it starts at 2960. Let's do the math. So 2964 at the end minus 2928. 29 is that right? 2928. Yeah, 36 bytes. So each one of these structs, so we had each fish struct now is going to be 36 bytes. So if we created 10 of these structs, we'd be using 360 bytes of memory. If we had 100 of them, we'll have 3.6 kilobytes. 100 of these fish. So then we had a I'm not going to embarrass myself with math. Okay, so you get the gist. So structs take up some memory. They're contiguous memories just like an arrays. And then when you embed a struct inside a struct, it's just allocating more memory one dimensionally, extending that struct with the necessary memory to represent that inner struct. So anyway, I'm tired. So let's continue tomorrow. I am going to commit this, and then yeah, thanks for sitting with me, everybody. If anybody's watching, I learned a lot. Okay, see you tomorrow.